everybody. I hope that this is working. But yeah, so today's class is obviously virtual. I'm sorry I'm not here. Friday we will be having James Allen Fox, the author of your textbook, to talk about ANOVA. So please make sure everybody reads chapter 8 in advance. And I believe your chapter 7 homework is due. So please turn that into him and he'll give it to me and I'll grade it and give it back to you guys. So the video is going to be two parts. Part one is going to be finishing up the lecture slides, and then part two is just going to be a video of me at a blackboard actually doing the problems. So last class we talked about. I'll go backwards a little bit, but we talked about when we have two groups, for example, in some kind of way, that we're interested in comparing their means between them. And we talked about how there are that there are several different versions of this problem. We can either be comparing our sample to some known population. That's where we would use a z-test, right? Because we'd have the population parameter information. Or more often, we're going to be doing a t-test. We're going to be comparing two samples either to each other on some measure, or we're going to be comparing a group of people on some measure twice. So that can be, for example, before and after some kind of intervention, some kind of criminal justice program, for example, or it can be matched pairs, so twin studies or husbands and wives being asked the same question. These are called dependent samples because they are related to each other. Whereas the first example that we talked about last class is called independent samples because they have no relationship to each other. So independent samples, like we talked about last class, can be men and women, students and teachers, Asian people and non-Asian people, Christians and non-Christians, whatever two groups that you're interested in for whatever reason, felons and non-felons. They're people that fall into exclusively different groups. They're mutually exclusive. So we talked about before how we're going to have a t-test and we're going to create a t-ratio based on the difference between means, specifically looking at the means of both of the samples and then dividing by the standard error of that lovely distribution of the differences between means. And unfortunately, we have this crazy equation that we have to do in order to get that. But basically, you plug the numbers into this equation, which again I will give you on an exam, and then you can go forth, get a t-ratio, and then compare it to your critical score like we talked about last time. Today, however, we're going to talk about a different version of the same sort of a problem, which is the dependent samples t-test. So when I have two groups that are, again, related to each other, so it's not men and women, it's men and women who are married and being asked the exact same question, and therefore we would expect their answers to be related. So if they're asking something like, oh, talk about how happy you are in the marriage, presumably if it's a happy marriage, both people will say, give it a high score, and if it's not a happy marriage, both of them will give it a bad score, right? Or we're looking at the same location before and after a hotspots policing intervention, right? So this version is going to have to be done a little bit different, but the idea of what we're trying to do in terms of comparing two different means is the same. So, instead of calculating the two means and then the two variances and then getting this one single standard error based on the sample size and variances as we did before with the independent samples, in this case we're going to need to get something called the standard error of the difference scores. And the difference scores are just simply taking one of the measures and subtracting the other. So I'm going to go through an example to show exactly what I mean, and then in the second video I'll go through multiple examples start to finish. So again, the hypotheses work the exact same way as they do for the independent samples t-tests. The null hypothesis is either that there is no difference between the means before or after or within couples, for example. and that indicates that there is that those two groups are part of the population, meaning there was no effect of the intervention. There's no difference in gender opinions on marriage quality. And the research or alternative hypothesis is that there is some sort of a difference. Again, here we are talking about a two-tailed test, and you can alter these in the same way as we did last class to talk about a one-tailed test. So the one-tailed, two-tailed test still applies for this as well. So let's go through an example. So here we have a Game of Thrones example, which I guess is a little dated now, but we have the Seven Kingdoms has had enough with the Lannisters' shenanigans, and they put each member of the family through anger management training. Were there significant differences in their behavior following the intervention? And then we have a bunch of the Lannisters. We have Jaime Lannister, Cersei, Tyrion, Myrcella, Lancel, Joffrey, Tommen, Tywin, Kevan, and Joanna. Some of them you may remember from the show, other ones they're mentioned more in the book, so read. But we have measures on their level of anger before and after the intervention, and we want to see if there was some sort of a difference. So here we are going to be doing something, as I mentioned, where we're going to be calculating difference scores. And we use the letter D just because difference starts with D, which is the difference between the two x's, before and after, or the dependent samples, right? So we're going to be calculating our standard deviation and our standard error based on the difference scores rather than looking at the two samples individually and then kind of pooling. Because that's what we're really doing in the independent t-test sample. Here, we're going to be creating a new distribution based on difference scores between them and then doing everything the way we would do for a z-test for the population. So basically, you can see that all you're doing is taking one score and then subtracting the other, right? And we represent this with D. So D is x2 minus x1, depending on whatever ordering you have. And D bar, or the mean of D, or the mean of the different scores, is the mean of one minus the mean of the other. Or you can just take the mean of the different scores and just calculate the different scores directly and take the mean of it. So this formula that I'm showing you, the second one, for the mean of the different, the standard deviation of the difference scores, sigma sub d, you can see is the exact same formula, the computational formula, that you're already used to from chapter 4, right? So all I've done is sub d in for x, and we know that d is just subtracting the two scores from each other. So basically we are just taking a little extra step to subtract them from each other and then doing our normal standard deviation. So for example, here I have all my people. I've created a new column, D, which represents the difference scores. So for example, I take x1, I subtract x2, so I'm taking the before, subtracting the after, and I get 2. 5 minus 3 is 2. For Cersei, 7 minus 4 is 3, and so on and so forth. I then take all of those different scores for the computational formula, and I square them. And so I get, for Jaime Lannister, I get 2 squared is 4, and so on and so forth. And then I can plug that into our formula for sigma sub d. I can also take the mean of d directly, rather than calculating the two means and subtracting. And so here, in this case, I have 10 people. The sum of the difference scores is 9, so my D bar, my mean of the difference scores, is 0.9. And when I sum up the squared D's, I get 25. And so I plug them both into my formula, and I get sigma sub D is 1.3. And again, here you have the hypotheses as we've had previously. Now, there's a very crucial thing that people often forget, because in the independent samples t-test you don't need to do that. And that is that the sigma d that we just got does not have a hat on it. So this sigma d, as you can see, no hat, meaning that this is just the standard deviation estimated from the sample, but it's not taking that and generalizing to the population. So just like we did with confidence intervals, we need to get sigma hat sub d. And so to do that, we do that just like we did before with the exact same formula of where I divide sigma d by the square root of n minus 1. There are 10 people, so I divide it by the square root of 9, which is 3, and I get an estimated standard error of the distribution of difference scores of 0.433. So again, this is just like confidence intervals, except I just have this one little baby step where I have to create difference scores. Then I take my difference score, I get my standard deviation, I get my standard error, the sigma hat one, and then I'm ready to actually plug it into t. So this is very important to remember, that you need this extra step of where you need to remember to do sigma hat sub d. Because with the independent samples t-test, the formula that I gave you already has the hat. So it's a one-stop shop giant evil formula that is scary. Here, we do not have that. We have one formula to get your regular standard deviation, and then you need to calculate the standard error like we've done in confidence intervals. So it is different in that there are two steps. So for the independent samples one, you only have that one step. Here we have two. So please keep that in mind as you go forward and do the homework problems. The other thing to keep in mind is when calculating the sample size is before we had two samples, right? We had men and women, so we had N1 and N2. Here, we have 10 people measured twice, before and after. The sample size is still just 10 because I have 10 people. It's not the number of observations because I have 2 observations per person, so I have 20 observations for 10 people, but my sample size is still 10. So then, of course, I calculate t, and then depending on my level of alpha as well as my degrees of freedom, in this case 10 minus 1 or 9, n minus 1, so 10 minus 1 is 9, I would then look up in the back of the book to see what the critical value of t is and compare. So if you do that for 0.05, you find that the critical value for t with degrees of freedom of 9, a two-tailed test with 0.05, is 2.262. And so, as the sample t-score of 2.078 is actually less than that critical value, right, or the absolute value of both is less than the absolute value of the other one, we fail to reject the null hypothesis and conclude that there is no statistically significant difference before and after the anger management intervention. Now, I have this shucking face because obviously, you know, the Lannisters are kind of evil. I don't know about an anger management program that's going to magically make them not evil anymore. I mean, they're blowing people up and stuff with wildfire. It's crazy. Right, so you could have done that without it. It's just a fun example. So that is the process of how we would do it. Again, in comparison to the first one, where I have to calculate, so in the independent samples t-test, I do still have x1 minus x2. Same thing for the dependent samples t-test. So the numerator for both t's is the same. The denominator here, which is the estimated standard error of the difference between means, is given to you in this crazy formula. So you just have to find that formula. So basically your steps are going to be find mean 1, find mean 2, find sample size 1, find sample size 2, and then to find both of their variances before plugging into this formula, getting this value, and then plugging into t. For the difference scores version, we are not going to be doing that. We're going to be finding the mean for the first sample, finding the mean for the second sample, calculating the difference scores, or D, calculating the standard deviation of the difference scores rather than each sample separately, and then finding the standard error of the difference scores before finally plugging that in. So you can see that they're very similar, but they are variations on a theme. They are slightly different. So it's important that you can identify which types of problems require you to do an independent or dependent t-test analysis. Now, when we do t-tests, there are certain assumptions that we are making to make the results of these tests valid. The first one is that there is independent random sampling, and that all of these events, all of these people in a sample are not dependent on each other. So in the independent samples t-test, right, that means that I sort of randomly sampled men and I randomly sampled women if I'm comparing men and women, and there's not some systematic thing happening. It's not that if I was comparing men and women in terms of GPA, let's say, it's not that I happen to sample women from the honors college and men who are on academic probation, because if I did that, then of course there's going to be a difference, but it has nothing to do with gender, right? For dependent samples, obviously I just said, well, the men and women are married, so they are dependent. But in this case, I am talking about them as a unit, as a couple. And so the couples have to be independently sampled from each other. So there can't be some sort of systematic bias that would explain the differences that we might find via a t-test. The other thing is that our outcome variable has to be interval or ordinal, that we're kind of quasi-treating as interval, with equally appearing values, right? So it has to have a reasonable scale. It can't just be, like people get 0, 1, or 2. Like that's it. There has to be essentially an interval ratio scale or an ordinal scale that we can treat as interval ratio. The dependent or outcome variable also must be normally distributed in the population. So we would hope if we know anything about this variable, we would assume that it is normally distributed. And if not, we need the sample sizes to be reasonably large. For our purposes, when we say a reasonably large sample size, that means an N of at least 30. So we need at least 30 for things to be generally normally distributed. And finally, the dependent or outcome variable is what's called homoscedastic, and that means that they both have equal population variances. That is to say that if we knew the true population variances for men and for women in this GPA example, they would be the same. So they have different means, perhaps, but they have the same variance. That is what is called the assumption of homoscedasticity. The homo meaning the same part, right? So these are our assumptions when we are talking about t-tests, and if any of these are violated, our findings may no longer be actually conclusive. Now, the other thing that I haven't mentioned here is that a t-test assumes that you only have 2 groups. Now, in many cases in real life, we will have more than 2 groups. So let's say I have some measure and I want to compare among people of different races. Well, it's not like there's 2 racial or ethnic groups, there's many. So I can't really do a t-test because I need only 2 groups. And that is where analysis of variance, or ANOVA, comes in, which we will be discussing on Friday. So that is it for the lecture. The next 2 slides represent the 2 problems I'm about to do on the Blackboard in the next video, and then I've added another problem. So I hope you all have a good week, and I will see you soon. Thanks. Bye.